All right, today we're going to look at section 3.4, and we're looking at another feature of graphs. So what we had been looking at in section 3.3 was where graphs were increasing and decreasing and where they had relative extrema, right? Peaks and valleys or maxes and mins. What we're going to be looking at now is how the graphs are shaped in another way, and that way is concavity. Now, you've probably seen concavity before. It usually comes up when you discuss parabolas. Our definition will look a little different because it's going to be more general, and it's going to relate to what we know about calculus. So, for a function that's differentiable on the interval I, the graph is concave up if the derivative is increasing, and it's concave down if the derivative is decreasing. So let me draw a picture of what concave up and concave down generally look like from the parabola standpoint that you have seen before. Concave up parabolas look like this. They hold water, right? You could actually put something in there and they're going to hold it. And then concave down parabolas look like this. They sort of dump water, or they at least don't hold it. So as we're taking a look at this, the description will make the most sense if we look at just sort of half of the graph. So just sort of think about the left-hand side of this graph. This graph on the left-hand side is decreasing, right? I mean, it's a decreasing graph. But it says that the derivative is supposed to be increasing. So what does that mean? Well, if you took the derivative, remember that's the slope of the tangent line. So if I took a tangent line to my graph over here, say, and I drew the tangent line, it might look something like this, correct? And be a very negative number. Agree? Okay, but as I get closer to the bottom of my parabola and I do another tangent line, the derivative is still negative, but it's not as negative as it was before, right? The slope there is a less negative number. So let's just put some numbers with it to sort of get an idea. Maybe this slope over here is like negative 10. But then at the slope down here at this point, maybe now your slope is negative 1. Well, if you go from negative 10 to negative 1, that's an increasing value, right? It's becoming more positive. And if you go to the other side of the graph, you can see it happening even more so, right? So if I'm looking at this point right here, just the sort of symmetric point on the other side, this would be my slope. And then, which is the derivative, right? And then if I come up here, my derivative is getting even more positive. So as I move from left to right, the derivative itself is increasing. It's first becoming less and less negative, and then it's becoming more and more positive. That's increasing. That's what it's describing. And exactly the same thing, but in reverse for the concave down. The graph is actually decreasing, the derivative rather, is decreasing as we move through the concave down region of the graph. Now, we can take this one step further and we can actually relate it back to what happens when we're looking at the function itself compared to not just the derivative, but the second derivative. So, when we have an increasing graph, actually, let me go back here for just a second. I promise I'll come back. What we learned in the last section, that is an increasing graph, it means that the derivative of that graph is positive. But the derivative of f prime is f double prime. So if the derivative, f prime, is increasing, then the derivative of the derivative, or f double prime, is going to be positive. And likewise, f double prime negative when it is going to be concave down or decreasing. And that's what this slide says. That we can test for concavity by looking at the second derivative. So instead of looking at where the first derivative is increasing and decreasing, which works, and we could do that, it's actually easier to look at where the second derivative is positive or negative. So if you have a second derivative that's positive, then your graph is concave up. And if you have a second derivative that's negative, then your graph is concave down. So our second derivative will directly tell us whether the graph is concave up or concave down. Just like the first derivative tells us whether the graph is increasing or decreasing. Now there's one more bit of title to this section that we haven't done yet. the title, I'll flip back here in just a second, said concavity, that's what we're looking at, and the second derivative test. Sometimes people get confused and think this is the second derivative test. This is not the second derivative test. This is a test for concavity. Okay, it tells us whether the graph is concave up or concave down. So we'll get to the second derivative test a little bit later, but this is not the second derivative test, even though it includes second derivatives in it. Okay, so we're going to take a look at finding places where it's concave up and concave down. So we have a function given to us, and it's a very straightforward function for our first one. It's quadratic, or not quadratic, I meant polynomials, I meant to say. It's a polynomial, which means finding derivatives of it's pretty straightforward and easy. So if we're looking for where the graph is concave up and concave down, we're always being asked what happens for the second derivative. So we need to find a second derivative. And in order to find the second derivative, we would find the first derivative first. So what is the derivative of x to the fourth? 4x to the third. How about negative 6x squared? Good. And then plus 2. Okay, everybody good with the derivative there? Wonderful. And if I was looking for increasing and decreasing, I'd use this derivative, the one I just found, and I'd look for things next. But I'm not. I'm asked about concavity, which means I need to do it again. So I need the second derivative. So what's going to be the second derivative then? Okay, everybody good? Okay. After that, it looks just like what we did with the increasing and decreasing. Okay, so we take two derivatives, but then we set it equal to 0, and we solve it, and we create a sign chart. All that's going to look just the same. Cool? Okay, so we're not going to actually have much different except that we do two derivatives before we get started in the same process we've already done. So we're going to set this equal to 0 and we're going to solve it. There's two different ways you could do this. It is quadratic. So you could try to do this with factoring, and there's nothing wrong with that. I'll show what that looks like first. The second way that you could do this is because there's only one x value, is that you could shift things to the other side and solve it that way. So let me remind you those two ways of doing that, just because we haven't done one like this in a little while. So we could take the 12 out, and we would have x squared minus 1. And then we would factor this as a difference of squares, x minus 1, x plus 1. If we set each piece equal to 0, we would find that x is equal to 1 and negative 1. Right? Okay. Or we could move the 12 to the other side. We would divide by 12. And we would take a square root. And we have to remember that when we take the square root, we put a plus or a minus. So either way, we're going to end up with positive and negative 1, right? And they're both equally fine. Okay, so these aren't called critical points, but they're acting like the critical points acted. They're going to do for us what the critical points did in the other cases. They're going to separate the number line. So we're going to create our number line. We're going to put the numbers on there in order, and we're going to test places in between the negative 1 and 1 and on outside of it, like in all three intervals. So what's a nice test point before negative 1? We might want to test. Negative 2. How about between negative 1 and 1? 0, of course. And then after that, 2. Okay, everybody good with that? Those are my three test points. And you could choose other ones, but they need to be in between there, of course, in those intervals. And we're going to test it in the second derivative, right? Because over here it tells us if the second derivative is positive, it tells us about concavity. If the second derivative is negative, it tells us concavity. So we need to know, is it positive or negative into the second derivative? So first derivative tells us increasing, decreasing. Second derivative tells us concave up or concave down. So we're going to put negative 2, 0, and 2 into this equation. You're welcome to do it in your calculator, especially when they become a little bit more complicated. You're welcome to do it sort of mentally as you're just looking at it as well, if you're able to see that one. Let's do the negative 2 first. If I put in negative 2 squared would be positive 4. 4 times 12 is 48, and then 48 minus 12 would be 36. In particular, it'd be positive, right? If I put negative 2 in, I get a positive. What happens if I put in 0? I get a negative. And again, these don't have to oscillate, but often they will. Caleb?
So just that they don't have to oscillate?
They do not have to oscillate.
Okay, so you do have to check them.
You do have to check them. So a lot of times they do oscillate, but they would not have to. I'll draw you a picture of one. If I don't have an example, I'll draw a picture later of one that wouldn't oscillate. I think I might have an example of one that doesn't, though, so that we will be able to see that. How about at 2? What happens when I put the number 2 in? Do I get a positive or negative? It's a positive as well. So when I'm writing my answer, again, it looks like what happened when I did increasing and decreasing, except that now I'm not talking about that. I'm talking about concavity. So that's concave up, where it's positive. So that's negative infinity to negative 1, okay? The interval endpoints, not the test points. And then I pick back up over here at 1 and go to infinity. And then it's concave down from negative 1 to 1. Okay, so this should feel familiar. You should feel like I kind of did this before, because you did. We did it with increasing and decreasing. The only difference is we're using the second derivative to make our decisions instead of the first derivative. Okay? All right. So this location, these locations, because I've got 2 of them, where it changes from concave up to concave down, or vice versa from concave down to concave up, has a name. And that name is an inflection point. So if we have a continuous graph and it's changing concavity, which we just did, right? Our negative 1 and our positive 1 on the, it changed concavity there. Then that location, at least the x value of that location, would be the x value of the inflection point. So let me just draw a general picture of how, oh, sorry, that wasn't what I wanted to do. Oh dear, now my thing's all gone. There it is. It's back. Okay. So if I were to draw a general picture of something that has an inflection point that you're familiar with, this would be a pretty good graph for one. If you were just eyeballing it, about right here is looks like we're changing from concave down, right? This is down, this one's up, and somewhere in between there it sort of switches places, right? This right here, approximately anyway, would be my inflection point. Okay, so let's actually just jump back real quick and grab your calculator and take a look. I don't have this drawn in, so I hope it works out okay. Take a look at problem number 1's original graph. Okay, so this problem we had over here. Sometimes x to the 4th graphs look kind of like parabolas. This one's not going to. I don't know what window I want. Let me just try a standard window and see what happens. Actually, a standard window looks great. Okay, so if you just do a negative 10 to 10 and negative 10 to 10 graph, it'll work just fine. And your graph will look something like this. It's not perfect. Let me shift it over just a little bit. At least a little bit more reasonable. Does it look something like that on your graph? Okay, it looks like a W, kind of drawn sloppy or whatever. And if I were plotting the negative 1 and the 1, it looks like this probably, the way my graph is probably about where the negative 1 is. It may not actually be on the x-axis. Mine looks like it is the way I've drawn it. The other one looks like it's about right here. But they look like places where it's changing in cavity. Can you see how it looks like it's concave up? Kind of a parabola looking feature right here. And then it's concave down in between my 2 red dots. And then it's concave up after that again. Yeah. So they don't all look like this graph, but they all have the same feature where you can see that somewhere in between there is a place where it's changed sort of the way it's opening. Okay. Oh, hang on. What happened here? Was that where I was? That's not where I was. That's the next slide, isn't it? Okay. Oh, I deleted a slide completely. That's wonderful. Now I got to go back and find how to put it back in later. All right, point of inflection. This picture works fine on this graph or this slide. So if we have C, f of C, and it is a point of inflection, there's 2 possibilities. It's either a location where the second derivative is equal to 0. That is the case on this one, right? The second derivative is equal to 0 at negative 1 and 1. Okay, that's one option. The other option is that the second derivative maybe doesn't exist. And that kind of makes sense again with what we saw happening with inflection points, or I'm sorry, with increasing and decreasing. We looked for places where the first derivative was equal to 0 or doesn't exist. And it separated locations where it was increasing and decreasing, and possibly a location where it had a max or a min. This is doing the same thing. It's just that those locations where it's equal to 0 or does not exist have a possible location of it having an inflection point. So notice how this is described. This tells you if it is an inflection point, then it is for sure going to have a second derivative of 0 or doesn't exist. What it does not say is that if the second derivative is 0 or the second derivative does not exist, that you for sure have a point of inflection. You can't go both directions. This is an if-then statement. It doesn't go backwards and go from the then to the if. Okay, some statements do. This one does not. All right? So we'll take another look at another one. You have a couple of options on this one. Option number 1, you can multiply everything out to start with, and that's not necessarily a bad option. It's only a power of 3. We could certainly do that. If we wanted to do it that way, then at the end of it, it'll look a lot like this problem, where then we're just going to take simple derivatives of some polynomials, okay? Option number 2, we can use a product rule because there is a product here. These two pieces are being multiplied, and we have a chain rule over here, okay? So as with everything in life, you give a little, you get a little, right? You're either going to get the easy derivative part of it with some messy foiling out, right? Or you're going to do the more complicated derivative, but the multiplying out is going to be easier. I don't care which one we do. You guys tell me what you would like to see. Do you want to see product rule and chain rule? Or do you want to see it all multiplied out? Be bold. Somebody tell me what you want. Multiply it out. Okay, thank you, Caden. We've got an option. We're going to multiply it out. No problem. Okay, so we're going to have to remember that when we do this, we have to write x minus 4 times x minus 4 times x minus 4. We cannot just cube the x and cube the 4. That's not a property. It doesn't work. So we'll take 2 of them at a time. You can even take the first 2 at a time if you want as well. So if I do the first 2 pieces, I've got x squared minus 4x. If I do the second 2 pieces, I'll have x squared. In the middle, I have negative 4x, and the outside I have negative 4x, so that's negative 8x. And at the end, I have 16. Okay, everybody good so far? All right. Now I have to distribute, again, kind of like a glorified FOIL, if you will. Move this down a little bit. Oops. So I'm going to take, I did it and then I shifted it back. How did that happen? There we go. I'm going to take the first piece, which is my x squared, and I'm going to distribute it through everything first. That's the order I'm going to do it in to make sure that I capture everything. So x squared and x squared is x to the 4th. X squared and 8x is negative 8x cubed. And then x squared and 16 would be 16x. And then I'm going to do the same thing with the negative 4x. It is a negative 4x, so I need to pay particular attention on this step to negatives. So I have negative 4x and x squared, which would be negative 4x squared, x cubed. I have negative 4x and negative 8x, which would be positive 32x squared. And then negative 4x and 16, which would be negative 64x. Did I get them all? I hope I did all my signs right. I was trying to be careful. I think I got the signs all okay. We're going to combine like terms, and we're almost done. So there's an x to the 4th. And then we have this 8x cubed and this 4x cubed. So how many x cubes do we have? Should be negative 12. Does that look okay? Negative 12x cubed. Okay, let's see. Oh, I only have one x squared piece. It's over here. Pink's a terrible color. How about we go back with red? So I have a 32x squared. And then I have 2 of them that have x to the, or a simple x in them, right? I have a positive 16x and I have a negative 64x. Okay, what will that give me? Negative 48x. Okay. So the multiplying out, it's not necessarily that it's all that hard, but it's really easy to lose a sign. It's really easy to mistakenly write down a cubed somewhere when you should have written down a power of 4 or something like that. So you do need to pay very careful attention to your algebra if you choose to do it this way. But the good news is we've done the hard part now, right? The messier part, and we get to do the derivatives easily. Kayla.
Is that 16x squared or is it just 16?
It's a 16x. Maybe it was supposed to be squared, though. I might have lost one, see? It should have been an x squared. You caught it. Thank you. All right, so let's fix that. Take a step back on these. See, I told you. Easy to lose things. Okay, so let's see. We had a couple of them that are x squareds then instead of a couple of them that are x's. Thank you for that. All right, so I have a 16x squared and a 32x squared. So I do have a 48, but it's a 48x squared, huh? Thank you. And then I have a simple 64x at the end. Okay. Do I have it right now? Oh, I hope so. Good deal. Okay, now we're ready to do a derivative. So we'll do our derivative. So somebody walk me through it. What do you got?
4x cubed.
Okay. 36x squared. Good. And then 96. Yeah, 96x and minus 64. Very good. Okay, but concavity is what we're working on, right? Okay, inflection points in concavity, so we need the second derivative, so we do it again. But it's a polynomial, so again, the process for the derivative is one of the more simple ones that we have. So what's the derivative of this one now? Excellent. Okay, ready, good? Now, if we had done this with the product rule, chain rule approach, and then we simplified what we had, it looked like this too. It doesn't give us anything different at this point. So at this point, we're back to matching what we would have done if we'd done it the other way as well. But in order to have a point of inflection will already automatically have a derivative that's 0. Now we have to check the concavity to make sure it really is changing concavity there, and it doesn't just, not. But we are going to set it equal to 0 as our starting point, okay, looking for concavity changes. So we set it equal to 0. Now, 12, 72, and 96. Are they all divisible by 12? 72 is. Does 96 divide by 12? I've got a nod. Okay, Jean, what do you have if you take out the 12 of all of them? If you divide everything by 12? What's 72? Is it 6 in the middle there? 6x. And it's 8. Okay. So we would love to use this one instead of this one because it's going to be easier to work with. Agreed? Okay. So we have options at this point in general. If it factors, that's usually what we try to do because factoring is our easiest of the options. But if it doesn't factor, what we might have to do on a particular problem is to use, at this point, a quadratic formula. Like that's an actual option that we might have to explore. I think this one factors. So let's try. Will this factor? Well, I've got an x and an x. What are my signs? The one at the end tells us that they have to be the same, otherwise I won't multiply to be a positive. And the one in the middle tells us they have to both be negative. So I'm going to have two negative signs. I need two numbers that multiply to 8 and add to 6. 2 and 4. Yep, -2, -4. Those will multiply to positive 8 and add to -6. So that's good news. Anytime something factors, that's a good news thing because that's our simplest option. And then if I set each of them equal to 0, this is going to give me 2 and 4, right? So I have possible points of inflection at x equal to 2 and x equal to 4. That's not an ordered pair 2, 4. That's x equal to 2 and x equal to 4. Okay, so space-wise, let me shift all this over a little bit so that I can get my number line in here. So we will have hang on. I wanted to shift it over and not be readable. It'll work. All right, so we're going to have our number line. Our number line is going to have a 2 and a 4 on it. And just like with the last problem, we're going to test the intervals between. So what's a good number to test before 2? 1. Or we could put 0 if you prefer. How about between 2 and 4? 3. And after 4? 5. So these are all very reasonable values to check. Where am I going to put the 1, the 3, and the 5? Into the second derivative, right? And to be honest, you could put it into either this version or you could put it into the version that you've divided by 12 because we didn't change any signs when we divided by 12. If we divided by negative 12, this wouldn't be a statement that I could make. But either of those versions will be just fine. So if you put in the number 1, so since we've got a little bit more of a detailed one, let's just put in our calculator. So we're going to do x squared minus 6x and plus 8. And into the table we go. We're doing 1, 3, and 5. So at 1, do we get a positive or a negative? Does anybody know? Positive. You're right, Kayla. How about at 3? It's a negative. And at 5? It's a positive as well. So they are oscillating. They are oscillating here. So positive means it's concave up, negative is concave down, and positive is concave up. This is the image to have in your mind. It says find the points of inflection and discuss concavity. So one of the things we're going to do is list the concavity features. Since we've already done that before, let's just do that first. So this is concave up from negative infinity to 2 and 4 to infinity. And it's concave down between 2 and 4. So that's the discussion of the concavity. When it says point of inflection means that the concavity changed. Did the concavity actually change at 2 and 4? It did. So because the concavity changed, I'm going to have 2 inflection points. It's not the 0.24. These are x values. It's an x value of 2 and an x value of 4. Now, how in the world am I going to figure out what the y value is? You got it. We're going to go back to the original equation. The original equation tells us what all the points are on a graph. Now, plugging in 4 is the easy one. What happens when I plug in 4 into this original equation? It's 0, because this piece in the middle becomes 0. So that's just 4, 0, right? The y value is 0. What happens when I plug in 2? I'm going to get 2 on the outside here. 2 minus 4 is going to be negative 2. What's negative 2 cubed? Negative 8. And then I have my negative 8 times the 2 at the beginning to give me negative 16. So this is negative 16. And feel free to use your calculator to plug them in, especially if they're messier than that too. But there's 2 inflection points. 2, negative 16, and 4, 0. Okay, so the other part of our title of our section said the second derivative test, right? So we're also going to take a look in this section at the second derivative test. And interestingly enough, while it uses the second derivative, it doesn't tell us anything about concavity. The second derivative test tells us whether we have maxes or mins. That's different. So take a look. If we have a function where the derivative is 0, not second derivative, the derivative is 0, and we use the second derivative, we can figure out if we have a maximum or minimum value. This is important. We are going to be looking for places where the first derivative is 0, and then we're going to be evaluating that point where it's 0 into the second derivative. So this combines things that we did in 3.3 talking about maxes and mins, with the second derivative stuff we've been talking about in 3.4. Okay, and I'm just reminding myself too, thinking about it, I still haven't shown you an example, Caleb, but I will. So remind me when we get done with our next two examples to go back and give you an example where we don't have it oscillate positives and negatives on concavity. There's a really simple example, so it won't be hard. Okay, you ready to try one of these? Okay. So this is your opportunity to use a little bit messier of a function. Directions tell us to find relative extrema. Okay, so when we're asked to find, or to use, the second derivative test, we are finding whether we have a max or a min. We're not finding anything out about concavity. The second derivative test tells us we're going to be taking second derivatives. So when we're finding relative extrema always occur when critical points are equal to 0. That didn't write. When the derivative at a critical point is equal to 0, or when the derivative at a critical point is equal to doesn't exist or doesn't exist. So relative extrema are still all about finding where the derivative is equal to 0. So that's where we start. We find our derivative, we set it equal to 0. So this one is, the way it's set up anyway, a very nice quotient rule. And it's a pretty clean quotient rule, so I'm going to keep it that way. The quotient rule says low d high, so low is x, d high, what's the derivative of the top? 2x minus high, x squared plus 1, d low, which is 1, all over low. Now, we need to set this equal to 0 and does not exist, so we need to clean it up in order to do that. Not only that, but it's going to be a lot easier to take the second derivative, which we will in a moment, if the thing's cleaned up, right? That's why we've been working on the algebra of cleaning up derivatives, is because moving forward and taking another derivative becomes lots easier when we do that. So let's clean this up. I have 2x squared. I have minus x squared and minus 1 over x squared. So this gives me x squared minus 1 over x squared. Is that okay? We need to set this equal to 0 and equals does not exist. The does not exist is really easy to see. Where in the world does this derivative not exist?
0.
At 0. So this one's going to happen when x is equal to 0. If x is equal to 0, and I try putting 0 and I get a 0 in the denominator, it's not going to exist. All right. The other piece, however, to set it equal to 0, what it really means is that the numerator has to be 0. Because if the numerator of a fraction is 0, the whole fraction is 0, right? 0 divided by 3, 0 divided by 5. If I have $0 and I divide it equally among my children, they all still get $0. Doesn't matter how many children I have. It's 0. So I need the numerator set equal to 0. So, close. We'll solve it with out factoring on this one. There we go. So this is x squared is equal to 1, and when I take the square root, just like you realized, we are going to get a plus or minus on that. So there are 3 critical points. Now, back in section 3.3, what we would have done is we would have put -1, 0, and 1 on a number line, and we would test at intervals in between, right? Okay, and there's nothing wrong with that. That's not an incorrect approach. It's just not the approach that's called the second derivative test. Okay? That approach is called the first derivative test. So if we're going to approach this with the directions given about second derivative test, what we're going to do next is we're going to figure out what the second derivative is. So let's do that part. There will be no sign chart. Maybe I should mention that here. When you see second derivative test, what it really is telling you is that there's going to be no sign chart. Okay, we're not going to do pluses or minuses on a number line. It's not going to happen. Okay, so what are we going to do? Well, we're going to take the derivative, and the cleanest version of our derivative, which was over here, is where I'm going to start. And we're going to find our second derivative. All right, so the second derivative is another quotient rule. It's low, d high. What's the derivative of the numerator? 2x minus high, x squared minus 1. D low, what's the derivative of my denominator? 2x. Divided by low. So x squared squared, which will be x to the fourth in a moment. And again, I want to clean this up, okay? So we've got 2x squared. I need to distribute the 2x, and I need to distribute the negative. I'll do it at the same time. So it'll be negative 2, oh, this is a typo. Please fix, it is 2x cubed, not 2x squared. Got ahead of myself. Okay, going back to distributing now. I'm going to distribute my negative and my 2x. That's going to give me a negative 2x cubed. And I've got the negative twice, so a positive 2x. And I'm going to divide by x to the fourth. So these two, of course, add to 0. The numerator is 2x. The denominator is x to the fourth. So one of these x's will cancel. This will leave me with 2 over x cubed in its simplest form. Now, if you left it with 2x over x to the fourth and continued from there, you'd be okay. It wouldn't be terrible. You'd just be doing a little bit more work, not a lot more. Okay, so we took the second derivative, right? I did the derivative, I set it equal to 0, and I solved, and I found 3 possible values. I mean, zeros and does not exist. I found 3 possible values. I found 0, negative 1, and positive 1. The second derivative test says now I take the second derivative, which I did, but there's no setting it equal to 0. What you see happening in this definition or this theorem is that you're evaluating it at the values of c that you found when you set the first derivative equal to 0. So you're taking each one of these points down here and here, if possible. That usually doesn't give us anything valuable, but it could. And you're trying to evaluate them into the second derivative. So legitimately, you're taking the second derivative and plugging in negative 1. You're taking the second derivative and you're plugging in 0. And you're taking the second derivative and you're plugging in positive 1. And what you're looking for, according to this test, is, do I get a positive or do I get a negative? Okay? Now think about it. What happens if you get a negative? What does the second derivative being negative mean about concavity? Is it concave up or it's concave down if my second derivative is negative? It's down. So this is a concave down graph. So again, parabola feature like, it would look like this. Do you see why a graph that looks like this would have a maximum? Can you see it? Yeah. That's why this works. It's because it is a concave down graph if the derivative is negative. And if the derivative is negative, then that means I'm going to have this kind of a shape. The second derivative is negative. I'm going to have this kind of a shape, and it's going to have a maximum value. And likewise for my minimum. If I have a concave up graph, I will clearly have a minimum. Okay? So if I plug in negative 1 into the derivative, so again, feel free to put the derivative in your calculator if you want. It's not a terribly difficult one. It's just 2 over x cubed, right? This is my derivative. Second derivative, I'm talking about. If I put in negative 1, 2 over negative 1 cubed, what does that equal? Is it positive or negative? That's what I really want to know. It's negative, right? I get 2 over negative 1 cubed, which is negative 1. This is negative. What happens if I put in 0? I don't get anything that's helpful, right? It does not exist still, so I'm not going to get anything from that one. And then I'm going to put in the number 1. So 2 over 1 cubed, or 1, which is 2, would be a positive. So what does a negative second derivative mean? Well, it means it's concave down. If it's concave down, what do I have? A maximum. If I have a positive second derivative, it's concave up. If it's concave up, I have a minimum. So what I have at this point now, besides the fact that I'm out of space, let me shrink it a little bit, is that I know I have a maximum at -1 something, and I have a minimum at 1 something. How do I find the corresponding something?
Plug it into the original equation.
Right, I put it back into the original equation. So let's go back up to that original equation. If I put in -1, what is -1 squared? 1 plus 1 would give me 2. So I'd have a 2 on top. So if I'm coming back up here and I'm putting in -1, I have -1 squared plus 1. That's a 2 on top divided by -1. So this is going to give me 2 over -1 or -2, right? So my y value, or my something that goes with -1, is actually -2. What happens if I plug in the number 1? I get a +2. And this is interesting. Okay, we're going to graph it so you can see why it works. But this is interesting because this is telling us that the maximum value, y value, is -2. But the minimum is 2. And that's weird because this 2 is bigger than this -2, correct? Why is that happening? We'll graph it and you'll see real quick why, and then we'll move forward. But if you take a look at this graph of the original function, so x squared plus 1 over x, standard window is just fine. You get the kind of graphs that you saw in probably an Algebra 2 course, or maybe a college algebra course if you've had one of those. And it looks something like this. Oops. Do you see that? Do you see why this is now a maximum, but it's below the minimum? Because it's relative, right? In a local area nearby, it's the biggest or it's the smallest, but not in the entire graph. So that can happen. Okay, last example that's in your notes, trig related, same directions. We're going to find the relative extrema, that means maxes and mins, with the second derivative test. So we take our derivative. What's the derivative of sine? Cosine. We keep the angle the same, and then we need to do the derivative of the inside. This is a chain rule. What is the derivative of x over 2? 1 over 2, right, it's 1/2. It might be a little friendlier to write this as 1/2 cosine of x over 2 if you wish. We're going to set this equal to 0. Notice the interval we're working on. It's the interval from 0 to 4 pi here. Trig functions, they typically give us intervals. I want to say always, but I don't want to say it that strongly just in case I'm wrong. But I think it's going to be always. You're going to see intervals, okay? Where is the cosine graph equal to 0? Between 0 and 4 pi. Well, let's just talk about cosine itself real quick. So if I have cosine on my unit circle, where in the world do I get cosine values that are 0? Cosine's x. So where's that going to be? X value is 0 here, right? Pi over 2. And 3 pi over 2. Now, technically, this is going to happen, at the angle measure equal to pi over 2, or 3 pi over 2. Maybe I should have made mention, this 1/2 at the beginning is irrelevant because I can multiply both sides by 2, like this, and get rid of it. So this is really just the cosine of x over 2 is equal to 0 still. Is that okay? The 1/2 at the front doesn't change where the cosine graph is going to cross at 0. And what happens when I multiply by 2 to get rid of the 2 that's underneath the x? Well, when I do that, I end up getting values, that are actually 0 and 3 pi. I'm sorry, pi and 3 pi, which is on the interval from 0 to 4 pi. That's why the interval went from 0 to 4 pi, is because you're going to get two values by doing this. Okay, no sign chart, right? No sign chart. Now we do a second derivative. So the second derivative, I already have the 1/2. The derivative of cosine is negative sine of the x over 2. And then the derivative of x over 2 is another 1/2. So I can combine this negative 1/2 and this positive 1/2. I'll have a negative 1/4 sine of x over 2. I take the second derivative and I evaluate it at the values that I found back up here in step 1. Second derivative at pi, and I do the second derivative at 3 pi. So I've got negative 1/4 sine of pi over 2, and I will have negative 1/4 sine of 3 pi, over 2. At pi over 2, still got my unit circle going on up here, so let's use blue. At pi over 2, right here, what's my sine value? It's 1, right? So this is actually, and again, you could use your calculator if you wish, it's negative 1/4 times 1. It's negative. And at 3 pi over 2, I get a negative 1, which means this whole thing is positive. Negative means concave down, so I have a maximum. Positive means concave up, so I have a minimum. So I have a maximum at pi something, and I have a minimum at 3 pi something. How do I find out what the something is? I put it back in the original, right? So I take my pi, I put it back in its sine of pi over 2. So what was sine of pi over 2? It was 1. And what was the sine of 3 pi over 2? Negative 1. So on this one, we actually do see that the maximum y value is bigger than the minimum y value. And that kind of makes sense because sine doesn't have any of those asymptotes that caused that last graph to break apart, right? It's a nice smooth curve. Not only that, but these are actually the absolute maxes and mins. They occur lots of times because sine graphs are cyclic, right? But they don't get any higher than 1 and they don't get any lower than negative 1. Okay. Let me do a real quick example to answer the question of, do we always get graphs that oscillate? This is a really easy one, okay? So we're going to create our function, and we're going to create it as x to the 4th. X to the 4th, super simple. What is my derivative? 4x to the 3rd. What is my second derivative? 12x to the 2nd. If I set this equal to 0, what do I get? Just 0, right? Yeah. So 12x squared is going to be equal to 0 when x is equal to 0. If I do this as a sign chart, because remember our question is about concavity. If I take a number before 0, I might choose, say, negative 1. After 0, I might choose 1. What happens if I put negative 1 into the second derivative? What will I get?
You're 1.
I'll get a 1 squared, which will be 1, and I'll get a positive, yeah. So if I put a negative 1 in here, I will get a positive 12. What happens if I put in a positive 1? I will also get a positive 12, right? It didn't oscillate. And I know I gave a really quick, simple example because I want to make sure it would really work, but there's lots of examples for which this would still happen. They just have to be specific types of functions, okay? So yes, they do not always oscillate. You really do have to check all the intervals.